Hey everybody, welcome to the rapid review on rotation. Thought I'd show you how I'm got this set up. Got a can of food, and I sort of tuck the phone in here on one side. Use that, and as long as the center of mass of the phone is supported, it won't rotate. And that's the idea. Now I just have to balance it. Let's see. Don't be suspicious. Okay. Okay, there we go. When an object rotates, the rules are the same as when an object is moving. And when we talk about motion, remember we're talking about displacement, velocity, and acceleration. We've talked a lot about mass, and mass describes an object's resistance to motion, to a change in speed, and in rotational inertia, describes an object's resistance to a change in rotational speed. Now, rotational inertia depends on two things. Rotational inertia depends on mass and distribution of mass. All right, there are a few more players. Let's talk about centripetal acceleration. It's toward the center. We're going to talk about torque. Now let's see, torque occurs when a force applied could cause the object to rotate. We'll mention a lever arm, and that is the closest distance from the fulcrum to the axis of rotation. And that was that phrase we wanted to keep using over and over. And then we have the kinematic equations. They become rotational. But the pattern is the same. The relationships are the same. All right. Let's get started here with circular motion. And let's start with an example. Cars are, I'll say like 1,000 kilogram, constant speed, around a flat curve, fast as it can, without skidding. Okay, that's the setup. It's the story so far. So one of the questions we ask is the car accelerating? The answer is yes. Yes, it is. Even though it's at a constant speed, it is accelerating because it is changing direction. Acceleration is a vector, has a direction, and that's one of the things that physics students know that the average Joe usually gets wrong. Okay, it's important. Let's draw a free body diagram, because that's what we do. And define the system, because that's what we do. Weight down, normal force up, and we'll have a frictional force toward the center of the track. Now, we're talking the system car, earth, or car and road, car, earth, road system. We're not talking about engine or anything. So let's define the system here in our description of forces. We have the normal force, which is the force of road on car. We have a gravitational force, also known as weight, and that is the force of earth on the car, and the force due to friction, which is the friction force, and that is the force of the road on the car as well. Now, it's a good idea to make this list with your free body diagram, because sometimes in free responses you get points for identifying or even using forces. So I recommend it. And plus it helps you think it out as you do it. Now, you might wonder, why is friction acting to the right? Like, shouldn't friction oppose the direction of motion? But yeah, okay, there could be friction or air drag acting backwards, but with the car moving at a constant speed, that have to be looked at as well by a forward engine force. And so, like I said, we're setting the system in a different way. So we're not looking at the engine or the tire friction, this one. We're looking at, well, the tire friction in the other direction. Anyways, you can email me. I can give you more information on that if you like. Let's do Newton's second law in each direction. Well, the friction force is equal to Newton's second law, like so. We know that acceleration is v squared over r, and we can write that somewhere helpful, maybe up here. AC v squared over r. I just stuck that there because for me, I know how to read the equations, so it does look like notes to me. All right, so mv squared over r, and we also know that friction is fun. So this is all equal to mu normal force. And boom, super useful. You can answer almost any question with that. And if you have to derive it, there you go. All right, the next player is torque. And the relationship is between force and distance. We can say even if force is at an angle, right? We can just break it up into its components. Okay, fx and fy, just like we would any other time. For example, if you had like a thin rod, axis of rotation on one end, and add this axis, had a force at an angle, you would label this as the x, or distance, or even radius in this case. But you would draw a separate diagram for your components. This is F. We've got Fx and Fy. And let's see, which of these could cause rotation here? That would be Fy, because this one's, we'd have an angle of 0 here. So Fy. And that would be F sine theta. That's also part of where we started back in, oh geez, January, when we first looked at torque. There it is. Can't, cause, rotation, f of x, totally wrong direction. You never know. They might ask a question where that comes in handy. All right, let's do another example. How about a bridge? I love the bridge. There's always a plank or a bridge. There's pillars or piers. And you can just label them if they're not labeled. Let's put some water down here just for fun. And let's add in some things we know. Let's have the center of mass of the bridge, FG, bridge, I guess, because we're going to have a person standing right over here. Let's have this pillar apply FA upward and this FB upward. We'll say the whole thing is 80 meters. And we'll say that this person is standing 20 from center. We'll say this person has force due to gravity, a weight of about, now let's not give you the weight. Let's just do a quick review here. Let's give this person a name. What do you say? How about, how about Ryan? We'll call it R. So Ryan has a mass of about 100 kilograms. And what else they tell us? The 20, we've labeled the rest. All right, so what is Ryan's weight? Well, weight would depend on what planet he's on. Let's label this Earth, just to be clear. If they don't mention it, it's Earth. And we would use Newton's second law. Or for special weight, we might say weight is mg, which is equal to 100 multiplied by 10, which is 1,000 newtons. So that would go here. And how heavy is the bridge? Well, let's just give it about 10,000 newtons for its weight. Make these numbers easy for us. Now we have everything set up that we need. Now you have to choose a fulcrum. It doesn't matter, the math will work out the same either way, but I'm going to choose side A. So I'm writing fulcrum question mark, choose a side. Let's say A is the fulcrum here. All right, now the force from the right side pillar, provides a torque equal to force and its distance from the axis of rotation from the fulcrum we called A. And if this was able to rotate, it's in static equilibrium right now, it's not rotating, but if it was able to rotate, it would push it up, and so counterclockwise. And in physics, for torque, counterclockwise is the positive direction. Okay. We've got the force due to gravity of Ryan. Ryan provides a torque equal to his weight and his distance from the fulcrum. This is not drawn to scale. Not to scale, because if the bridge itself is 80 meters, the center of mass would be 40, and if he's 20, I should have drawn him in the middle. A little bit would have been better, right about here. Anyway, so he's 20 from here, 20 meter. All right, and if this were allowed to rotate, he would be pushing down and it would move clockwise. And we would say that's negative torque. All right, so we've got this force up from pillar B. We've got our force of gravity, or the weight from Ryan standing there. And we need now F of G for the bridge. F of G bridge provides a torque equal to its weight, 10,000 Newton, multiplied by, all right, and if the bridge is 80 meters, at the center of the bridge would be 40. So we'll multiply that by 40. And if it was allowed to rotate, it would rotate clockwise, and that would be negative. Those are all the forces that could cause rotation. Now we're just gonna set them up in a way that makes it easy for us to see if it's static and to prove it mathematically. We'll say set the positive equal to the negative because it's static, so the net torque is 0. So that's what we're looking at. And we would end up with, let's see, FB80 equal to $20,000 Newton meters. Let's remind ourselves the torque units, and plus 40, 400,000 Newton meters, and you could solve for the force there and find the force from the pillar. It's a common question. All right. Rotational kinematics. The 3 equations. The final angular velocity is equal to the initial angular velocity plus the angular acceleration multiplied by the time. The displacement is equal to angular initial velocity multiplied by time plus 1/2 angular acceleration multiplied by time squared. And the final angular velocity squared is equal to the initial angular velocity squared plus 2 multiplied by the angular acceleration and the displacement. And these are used exactly the same way as the other ones for linear motion. What I want to spend some time on is rotational inertia. Okay, you should look at 2 things, remember. One of them is mass and one of them is how far away the mass is from, there's that phrase again, the axis of rotation. Use that as much as you can, or where appropriate, but definitely if they ask a rotation question, you should be saying axis of rotation at least once or twice. There are three particular ways we can look at to get rotational inertia. Let's see. For a point particle, we just say that the rotational inertia I is equal to mr squared, which would give a unit of kilogram meter squared. The second way is like a ball or a disc or a rod or a sphere or anything like that. They'll give it to you. But I bet you already memorized a couple. And if you're looking for something to help you that's doable, go ahead and memorize a couple of those. But they are supposed to give that to you. Or you can always derive it from the geometry in the back. Number 3, a system of several objects. Just add them together. Okay, it's a possibility as well. For example, let's do A, B, and C. Let's have 3 identical rods and 3 identical like little masses and 3 different grips. Let's see, so this one would be like if you're holding it at the bottom, and here hold it right in the middle, and for C let's hold it at the top. Excuse my little drawings. All right, let's lay some groundwork here. Let's say they are all 1 meter long, uniform. That makes it easier. They're all 200 gram bars, and they each have a 200 gram mass. These little things with different grips. Okay, they'll tell you that the rotational inertia for a rod, I should write that here. Rod is equal to 1/12 m, and we'll use L squared. And that is like on an end. But if you hold it at the center, it would be 1/3 ml squared. No, that's at the center. And it's 1/3 ml squared at the end. And they would tell you this, given. Okay. All right, what can we do with this? We can do a couple things with this. But let's find out the rotational inertia of each of these cases. First, look at A. We have the rotational inertia of the rod. Holding it at the end, 1/3 ml squared. That's 1/3 0.2 1 squared. 0.067 kilogram meter squared. Okay. What about the rotational inertia of the little mass? Well, it's not rotating, so no contribution, or mathematically R is 0. That makes I total for case A 0.067 kilogram meter squared. Let's do it again. It's time for B. Rotational inertia of the rod when he's holding it in the middle will equal 1/12 ml squared, which 0.017 kilogram meter squared. Rotational inertia for the mass, not rotating, R equals 0. Again. If R equals 0, then I equals 0, right? Okay. So I total is 0.017 kilogram meters squared. Let's do it again. This time for C. Rotational inertia of the rod is 1/3 ml squared, which is 0.067 kilogram meter squared. We already did that. Now the rotational inertia for the mass, aha, not 0. But that's just ml squared, treated like a point source. And that is 0.2, 1 squared, 0.2 kilogram meters squared. Okay, so total for C is equal to 0.067 plus 0.2, sorry, equals 0.27 kilogram meters squared. Boom. Now the calculations are not the point here, okay? Calculations can help you rank it if you don't intuitively see how this works yet. So I'm going to say calcs are not the point. This is probably a ranking question, in which case we would have the rotational inertia for C greater than the rotational inertia for A greater than rotational inertia for B. Next up, Newton's second law for rotation. Let's say, just like linear acceleration, is caused by a net force angular acceleration is caused by, I know you know it, a net torque. That's right. Torque is the product of rotational inertia and angular acceleration. We can make a note that if more than one force is applying torque, then add them up. Okay. For example, a turntable, like a record player, spinning disc of mass M and radius R is attached to a motor that provides torque. All right, let's say a student predicts five seconds for the turntable to speed up from rest to reach max speed. Well, let's say max rotational speed for the record. But, dun, 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 when the student measures the time, they discover that it actually takes 6.8 seconds to reach maximum rotational speed. Very interesting. So in this type of question, in a free response, they'll want you to like design an experiment. And remember, designing an experiment should have 3 or 4 things in it. Most notably, multiple measurements. Just blanked. What is it? Multiple measurements. You say it. Tell me. Yep. Attend to the question. It's good to declare how you're going to analyze it. You'd say something like, in order to blank, I would measure blank and calculate blank and analyze this way, usually with a graph or a percent error or something. You should be able to describe how to perform such a measurement in the lab too. There's so many ways of doing this. The idea is to make many measurements of rotational speed until the rotational speed doesn't change, right? Think about precision. Rotational speed could be measured with a video camera, a protractor. You could run the video frame by frame to see how many degrees the turntable advances per frame, or tape a tiny piece of paper to the edge of the turntable and have it trigger a few photo gates. You could measure the angle between the photo gates, and the photo gates tell you the time for it to traverse that angle. So you should think about when they ask you to do a design, go ahead and imagine yourself in class in a group with your favorite group mates, and you're listening to somebody say the best idea ever. And then you can hear other people chime in just to make sure you have everything. The most obvious issue here is that the torque by the motor is not necessarily the net torque. Let's write this down. Now, they didn't say net torque. And you know that's how these questions are. It's all about either one word that's there or one word that's not there in this case. What about friction? Think that played a part? They didn't say no friction. It should be able to assume it. But since it's like a design lab challenge, you can definitely and should think about friction. When they say real world or in the lab, go ahead and play with friction, or at least mention it. So if that's the thing, let's think it out. What would it be? So the real value will be lower. And net torque is IA, so A is lower. Okay, and by the kinematic equation, that means that the time is longer. And so this justification would explain the discrepancy between the prediction and the actual measurement. Okay? All right, two more. Angular momentum. True? Yeah, I think that's true. There are two ways to look at angular momentum. For a single point, you could say L is MBR, like a point around something, or an extended object. We would say L is equal to the product of the angular